Okay. All right. So by doing this, as you guys already can tell, for this, we say this wave function carries two variables. Our idea is if we consider the rotation on the sphere as a stacking of the rotation on the plane, you're stacking them around the theta axis. And that's why we say we can separate this using the separation variable. One is carry the information on the rotation of the plane. The other we introduce the stacking along the theta axis. And then we plug into the Schrodinger equation. And we actually, literally for this, yes, we can separate them. So we separate into the two wave functions. One is the phi, that is literally the solution for the rotational motion on the two-dimensional plane. And then you have the theta form. Okay. Very good. All right. So, as I'm going to write over here, so then we separate into the two equations. Each depends on one variable, and we already know the solution to the first equation, that is really the solution for particle rotation on the ring. Then we will have a second one we can solve for. So the solution for the first one is really the solution for the particle rotation on the plane, which equals to constant root of 2 pi times the E function I m7l phi, and phi from 0 to 2 pi, m7l is your quantum number for that rotation on the plane. Now, mathematically, you can also solve for the expression number 2. If those of you who had the opportunity to learn this, then these are really the solution they call associated Legendre functions. Okay. Once we have a mathematical solution, we also need to impose the boundary condition for the theta from one pole to the other pole. In order to do that, we will introduce a new quantum number L. But the quantum number m7l and L, through your calculation, they are linked. Okay, so it sounds a lot to tell you, but all right. Remember, we introduced quantum number m7l with the particle on the plane. It's because the wave function has to return to the same value when you add one revolution. So basically, we impose the boundary condition. That's how we introduce quantum number m7l or n or b, whatever. Now, for this we introduce m7l that equals to integer number. But if we solve it for the second part of the expression, you also have boundary condition at the pole for that wave function. Now, in order to solve it for it through the solving process, we will introduce a new quantum number that is L. Okay, so therefore, for this two variable wave function, we will have two quantum number. But the quantum number L and the answer L, they are linked. Now, why they are linked? Look at the expression. In this expression, solving for the theta, you carry the information of the answer L. Now, I'm not going to go to the detail of this. So, how do these two link? L can take from 0, 1, 2, positive from 0, 1, 2 integer numbers. At each L value, answer L can take from the negative L, step up by +1, go all the way to the L values. So those two quantum numbers are linked. All right, at each L value, answer L value, also integers, take from the negative L. Now L equals to 0, 1, 2, 3, keep going. From negative L, the negative L plus 1, and keep going, then you go all the way, then you go all the way, you go, at the end is the L minus 1 and the L. Alright, let's say if L equal to 2, then the answer L can take from negative 2, negative 1, 0, 1, and 2. Right. Okay. Alright. the total wave function. So the total wave function contains two components. Alright. Now we use a C to represent the wave function. But in this case, the function only carries the variable for the angle, so we use a Y to represent. There's really nothing fancy. And in this wave function, we will have two quantum numbers, L and M sub L. Alright, and I said M sub L values is constrained by L. Now L can take 0, 1, 2, keep it going, and M sub L, as I have mentioned, it has two L plus 1 values on each L values. Right. What do you think? Do you feel massive time? But at least I show you how you can do the separation of variables and to do all of this. So good. Okay, now I finished the whole case study for the wave function. On Friday, we will pick up from here, review a little bit, and then we will show you the quantum state, then we will do some calculations. Okay, so I will not see you guys